One of these years I'll learn to dry run my talk. So the motivated bottom-up approach. Motivated is critical. In fact, when my book came out, he already mentioned my book. I'm not going to plug the book, but there is a reference to the book somewhere in there because I need to let you know that I've written a book so I no longer have credibility. See, I now have a book that if you believe my way, you'll buy my book, I'll make money. Don't buy my book, steal it, so I don't make money. It's not about making money, it's about believing in the model. So one of my favorite educators, one of the teachers is Mike Clancy. Mike was one of Knuth's students at Stanford, and he was part-time teaching the introductory courses at Berkeley. So, every 10 years I leave and go someplace else, and when they steal me, one of the perks is instant tenure, and I'm old, so I hear 10 years, and then after 10 years I assume I'm supposed to move on to another school. So I spent 9 years at Berkeley, and Clancy was on the faculty then, and he was teaching some of these low-level courses, and I bumped into him, years later, shortly after the book came out, and he had looked at the book, and he says, this is great stuff, but how do you keep them interested? If you're in there in the bowels, don't they get bored? And I said, I never thought about that. Then I looked at my table of contents, and I realized that I wasn't bottom-up. So it's now like 900 to 100. So it's still overwhelmingly in favor of this top-down. But it's slowly happening. Cornell, Santa Cruz, Georgia Tech, Purdue have all jumped on my bandwagon. So why the most start at the top? So I try to see what some of the explanations could be. One thing I think is a misunderstanding. Misunderstanding design versus learning. So top-down design is correct design. You don't want to design bottom-up. If you design bottom-up, you'll end up with the old design and a pimple on it. Okay? You want to design top-down. You want a clean sheet of paper. You say, okay, what is my problem that I'm trying to solve? So top-down design is correct design. But when you design, you already know the components. Okay? When you're learning, you don't know the components. So design is top-down after you understand the components. Another glitz to woo students into the major. There was one university where you had EE and CS, and EE was trying to decide whether to use my book in the freshman course. Bottom up. We're going to teach a machine language. And by the way, if you start with machine language and then you go to assembly language, they'll love you, that they don't have to deal with zeros and ones anymore, right? As opposed to the other way, and they've grown over assembly language. But, in the LC3, in my machine, 0001 is add. And then we graduate to assembly language. ADD is add. Wow. I still don't know all the opcodes of my LC3. There's only 15 of them. I don't know them all. Why? Because why would I ever want to memorize? Most of them I know by now because I've taught it enough times. But never memorize what you don't have to. So the EEs were thinking about using my book. CS was using Java with all the glitz and showing, bells and whistles. And so EE decided not to do it, but do Java also because they were afraid they're going to lose enrollment to the computer science department. It's easier to find instructors for Java. One of the problems with doing it my way is the instructor really has to understand it to teach it, and that's problematic. The want ads ask for Java programmers. That's another reason, the kid's mother wants him to be, make money when he graduates. So want ads ask for Java, so we will teach Java. But these are freshmen. They're not going to graduate for 4 years. By the time they graduate, it won't be Java anymore. It'll be C#. Okay? So what's going to happen 4 years from now, we'll be teaching C#. Not now. 4 years from now. Because that'll be the sexy language of the time. Except by the time they graduate, the sexy language will probably be D flat. Okay? So you can never solve this problem of trying to prepare them. Chasing the want ad should be an obvious mistake. Then there's this thing about object-oriented. It's a productivity enhancer, which it is. There's absolutely no question. Object-oriented, the higher the level of abstraction, the higher the productivity. But It better be the case that everything below works, right? Because if it doesn't, you got problems. I was in the financial center of New York, and I needed a cab to the airport, so I get in the cab, and I said, LaGuardia. LaGuardia, 4 syllables. What could be a higher level of abstraction than that? And the guy's going up the East Side Highway, and he takes me over, I don't know how many of you know Manhattan, but he goes, bleh. So here I am in the financial district, here's the airport, there's a Midtown tunnel, takes no time at all, and 10 o'clock in the morning, so there's no traffic in the tunnel. See? But I wasn't in control of the automobile, he was. So even though I could do this high level of productivity airport, or LaGuardia, I was at his mercy. You know, you want to get to the airport here in Pisa, so you get into the cab and you say, airport! And he's driving and he's driving and he's driving, and all of a sudden you look out the window and there's the Cinque Terre, you know. You're not in charge, you know. You may miss your flight, by the way. If you go by way of the Cinque Terre to get to the airport in Pisa, you may miss your flight, and you won't be happy about the fare. So object-oriented, it is absolutely a productivity enhancer. Abstraction provides that. But as far as object-oriented, so this guy, C.V. Ravi Shankar, used to be a colleague of mine in Michigan. He now teaches at Riverside. He has a quote which I like a lot, which is, information hiding is all very good, but students need to first have some information before they start hiding it. So how I made it happen at Michigan, first at Michigan, now at Texas, and since then the world. So at Michigan, the faculty were really unhappy because the kids weren't getting it. They just did not get the first programming course. You know, pointers, in fact, I think Sean and I agree at least that it's important for the kid to have an idea of how memory works, that there's an address and a value. A 6 in location 4 is not the same as a 4 in location 6, and he and I agree about that. You know, I think they need more foundation. He absolutely agrees that at least that much foundation. And so, in fact, if you don't understand that 4 in location 6 is different from 6 in location 4, you have no chance of mastering pointers. You know. So pointer variables are hard because the students don't understand how memory works. And a lot of these freshman courses, they don't understand how memory works. And recursion is magic. You know, but if you do this bottom-up approach, you know, in C, I would say the soul of C is function call. Right? And so function call, you need a linkage. Well, recursion is just you adjust that linkage. And in fact, what's his name? Lilja at Minnesota decided to adopt my approach, used the book. He says he taught him recursion. It took him 20 minutes to teach recursion. It came after teaching function call. It was bottom-up. So by the time he got to the high-level stuff, they had the underpinnings. They knew what an activation record was. And so it took him 20 minutes to teach recursion. He assigned them a problem to write a program for, and he says they all got it. He says, I am sold. So pointer variables are hard because they don't understand how memory works. Recursion is magic because they don't understand the linkages. And then this concept of build on what you already understand has a certain ring to it. And that's how I was able to get it to work at Michigan, and since then it's been good. What I want to do in the first course is get rid of the magic, pointer variables and recursion, build a strong foundation, continually raising the level of abstraction. But first, in fact, I've already told you that I wrote a book, and so I need to say that because my credibility is out the window, having now an economic interest in my model, which I really don't, and it's called Introduction to Computing Systems, From Bits and Gates to C and Beyond. I did it with one of my former PhD students who TA'd the course the first time I did it at Michigan, and the publisher's been pushing for a 3rd edition forever, and hopefully we'll get it out this year. I've been reluctant to get out the 3rd edition until I really had a major benefit. I'm not a fan of this every 2 years you do a new edition to wipe out the used booksellers. But we are at a point now where we really do need to do a third edition, and hopefully it'll get done. My mantra is start with what they know. The transistor is a light switch. Kids have been doing transistors, have been doing light switches since they were 2 years old. Boom, lights on, boom, lights goes off. They understand that. They can build on that. They don't have to question that. That's what's important, a foundation that they understand. Not quantum mechanics. I always get the question, well, if you really believe in bottom-up, why don't you go to quantum mechanics? Well, two good reasons. One, I don't understand quantum mechanics, you know, Heisenberg, the cat is dead. You open the box, but no, when you open the box, the cat died. I still don't get it. I'm not bright enough. That's okay. The kids don't have to understand Heisenberg in order to, learn how computers work. So I don't start with quantum mechanics. I start at the point where they need, which is the transistor as a wall switch. Choose a computer model that is simple. I'll talk about my LC3 in a moment. As the genius said, make it as simple as possible, but no simpler. Albert Einstein. And he's right. So the LC3, even though it's simple, and you'll see there's a slide with the entire instruction set on it. It's on one page, inside cover of my book. So you can grok it. It's not a matter, it's not like this thick. We had one of my colleagues teaching the course. He said, the course would be fine, but why do you use the LC3? LC is little computer. Why 3? Because I got it wrong the first time. And the second time wasn't much better. See? I think now I understand it. Because, he says, why don't you use x86? The freshman course, x86, give me a break. Okay? You make it as simple as possible, but still rich. And that way they get it. That's what's important, is getting it. And continually building on 10 minutes? Really, already? You didn't shorten me, did you? Continually raising the level of abstraction, memorizing as little as absolutely necessary, trying very hard to not introduce magic. Get rid of magic. Someday I'm gonna make up these, it's gonna be like this with magic, and then The motivated bottom-up approach. I've already given you a little hint of it. So an overview, and these are kind of the order of treatment. Number one is an overview, and then operations on bits, bytes, etc., and then we go to the transistor, and from there digital logic, finite state machine, von Neumann model, and then the LC3 instruction set. Now they're ready to program and debug. In fact, the first program they debug. In fact, one of the clowns that reviewed my book when it first came out said, why do you teach debugging so early? You don't really have to know how to debug until you've written 1,000-line code. So my answer is he's clueless. You learn debugging right from the get-go. Right? And in fact, if you do it my way, they can debug their own programs because they get it. And then assembly language programming, physical I/O, keyboard and monitor. Simple, but not too simple. You hit a key, the ASCII code goes into the data register, the ready bit gets set. And then on the program control, you can grab that value and put it wherever you want and work with it. Right? Monitor, same thing. You write to the display register, and then the electronics put it on the screen. Right? And there's a synchronization involved here, from the computer that runs fast to the human that runs slow. And then subroutines, calls, traps, interrupts. So you don't do it on the program control. When you hit a key, sets the ready bit. If the interrupt enable bit is set, it preempts the program that's running. You take the interrupt, and you go through the interrupt service routine. And you have that interaction, by the way, with the system software. And then C, and then programming in C. That's the course, motivated bottom-up. So here's a picture of memory. It's not 2 gigabytes. It's 4 trits, right? So I've got, this purple on the left is the decoder. And since I've got 4, I need 2 bits of address. And the rows are word lines, and there are 3 bits in each row. And those other 3 purples are all, so I'm a guy, so that's purple. The women will tell you what color it really is, And those are muxes that will source the appropriate bit of the bit of the appropriate word line. And before they get there, they've learned about transistors, and they've learned about gates, and they've learned about muxes, and they've learned about decoders, and they've learned about gated latches, and so they put it together in, wow, memory, and so you really get it. And that, we're talking, this is like one lecture, lecture and a half. Here's the ISA finally. So there's one arithmetic, it's called add. You want to subtract? Take the negative and add. You want to multiply? Add. Right? So I don't waste opcode space. I only have 4 bits of opcode. I got a 16-bit word, 4 bits of opcode. And the rest of the bits, it's a load store machine. So before you can add, you have to have the sources and registers. And the add takes 2 sources. One can be an immediate. If you look at the top 2, you see that they're both add. You'll notice bit 5 is a 0, identifying a register, and bit 5 is a 1. The low 5 bits as an immediate gets sign extended out to 16 bits before it gets added. One arithmetic. 2 logicals. I could have only had one logical, NAND. That's complete, as you know. But I decided that was counterintuitive for freshmen, so I have 2. Not and and. 2 logicals. So don't waste a lot of opcode space on unnecessary opcodes. Several loads and stores. I have load immediate, store immediate. Why? Because they're freshmen, and what I want to do is if I teach them load immediate, load indirect. Load indirect and store indirect. Because if I teach load indirect and store indirect, what does that say? It says go to that address, and what you're going to find there is going to be the address of where the data is. And then later on, when you teach them pointers, you just say, hey, remember when we talked about load indirect and store indirect? So you already know pointers. Piece of cake, right? And so there are flavors of loads and stores. There's PC relative, and there's indirect, and there's register plus offset. So I waste 6 opcodes on loads and stores. And if you look through there, you'll see there's a trap instruction. So early on, you want to do I.O., you trap, you give it the proper trap vector, and the operating system does the I.O. for you. By the end of the semester, you actually look through the LC3 code that implements those trap service routines for you. Right? 1 page, the entire instruction set, 15 opcodes. Used to be 16 opcodes. You notice the one at the bottom says reserved for future use. I resisted using it. It turns out that I had 16 opcodes. I had a subroutine call, so I had a return. The call return mechanism puts the return address into register 7. And so this freshman raises his hand and says, why do you need a return instruction? Why don't you use just a jump instruction with the return address loaded into register 7? I said, you're right. And so I got rid of the return instruction. And in the assembly language, return is the same instruction as jump through register 7. 8 registers in the machine. Okay, so here's a picture of the entire data path of the machine. Pretty simple, you know. 5 minutes? Okay. And you'll notice there's a register file, there's an ALU, there's an adder, there's some muxes. There's very little there to implement this instruction set. So they can get it. State machine for the whole machine. You know, 35 states. And so they see, you know, sequencing through. And they get it. Maybe I'll go through this very quickly. What ISA should come first? And in my view, there are 4 models. The Mickey Mouse model, I call it the art history model, which I won't. There's some silly books that think they're teaching and they're not. That are just too simple, and you actually don't even program them. And then a rich but small ISA that students can really grok and use, like the LC3, which I think is the correct answer. A subset of a existing ISA. One of my colleagues suggested a subset of the Motorola 68000. And the last thing is a serious ISA like the x86. And for those of you that are software people, what I decided to do is liken these to what programming language should come first. So the Mickey Mouse model, I would say, is a template language not unlike Java. And the correct answer is something like Worth's Pascal. And the subset is kind of like a subset of PL1, which is a favorite approach about 30 years ago. And a serious ISA as your first step, something like C. And the point is that the operative word, in fact, I should have put it in a different color, is the title. It says what ISA should come first, not last, first. Where do you start them? You start them simple, but no, not too simple. Arguments for using a production ISA. Valvano is one of my colleagues who loves the freshman course, except for the fact that I use the LC3. He would really rather we use the Motorola embedded controller, the 6812. And he says students are wowed by seeing something real. And the other people that want to use a production ISA is Randy Bryant, Bryant O'Halloran. He says that students learn better if they're writing code that runs on real machines. And I, of course, don't agree. We chose the LC3. It's a subset of a real ISA. It's not a subset of a real ISA. Real ISAs have uglies. When you design a real ISA, why do you design an ISA? Why do you build a chip? To make money. And so there's always going to be a place where elegance conflicts with making more money, and elegance loses. When you design the ISA yourself for teaching, you don't have that problem. And so you can do the right thing rather than these uglies. A clean sheet of paper allows you to make every decision pedagogically. We can still get the wow effect by simulating and have the students write programs which then run on the simulator. And the fact of the matter is, when you have a real machine, you're really away from the machine to the same extent that you are with a simulator. So I don't see it as any different. Students can debug their own programs, which is critical, and we can still build on this in later classes. This tells how the LC3 has evolved. I think I'll skip it. What we left out of the LC3 is endianness. So a byte gets stored in the full word, 16-bit word addressability, not byte addressability of memory. So you don't have to worry about endianness. In the senior year, we talk about the LC3B, which is the byte addressable LC3. Then we introduce endianness. But freshmen make it as simple without making it too simple. We left out lots of data types. We only have integers, 2's complement integers, no floating point, no bytes. LC3B, we have load and store bytes. And we left out lots of addressing modes. VAX had 13 addressing modes in hardware, which the software people liken to about 40 addressing modes. You don't need it. There's continual pressure on us to add a multiply, shift instructions, and a carry bit. Carry bit would be useful for doing long arithmetic, but I've given up on that because I want it to be simple enough that they get it. What we've learned is don't succumb. A one-page ISA means students can learn. It can be rich without being complicated. Simulation can create this wow effect. And then the follow-on activity, which has already happened, the LC3B in the senior year, which has byte addressability, we got rid of indirect load and store, replaced it with load byte and store byte, because by the time they're seniors, they don't need indirect. If they haven't learned pointers by then, forget it. And then we're dealing right now with adding privilege so people can write operating systems for this. The LC3B is taught to seniors and graduate students, and the students add virtual memory support to it. They add interrupt and exception handling support to the implementation. The NOT instruction has become an exclusive OR. I've already said word addressing becomes byte addressing, which means we have to deal with endianness. And I already told you the indirects are scrapped, and we have a comprehensive shift instruction. The benefits of the bottom-up approach: we get rid of magic. We minimize memorization, which maximizes understanding. Students build on what they know. They debug their own programs because they can. I've talked to many classes where they teach the high-level language and they're forever upset with the fact that students never learn how to program. And why? The student makes a mess, goes to a TA. TA does the first half of the program for them. He says, okay, now I've got you started. You finish it. What does a kid do? Goes to the other TA. Okay? And he graduates without ever having written a program himself. Students end up with a broad-based foundation, and they love it because they get it. I'll tell you, the emails that I get, incredible, you know, because they get it. And the teachers love it because the students get it. Extra benefit is it unobtrusively, not intentional, but I look back after it and said, you know, I'm really giving them a breadth first approach to the whole business of computer science and engineering. data representation, logic gates and structures, finite state control, basic computer organization, assembly language, and how an assembler works, physical I/O, interaction of the application software with the OS, all in that first semester. What I've learned about students: freshmen, I already told you, can handle serious meat. They don't need glitz. Computer organization can begin with freshmen. Students will debug their own programs. The bottom-up approach eliminates memorization. And as I already told you about my trip to Yorktown, memorizing 95% correctly gets you nowhere. And by the way, good students memorize for only one reason. About education, engineering education, there is no substitute for the student designing it wrong, because we all design things wrong, debugging it himself or herself, fixing it, and seeing the working result. And wow! Avoid the latest fads. Abstractions are fantastic after you understand what you're abstracting. By the way, does motivated bottom-up work for everyone? This is a thing to, what if you just want to be a gopher programmer, you know, just do what you're told, be a coder, not really a programmer, then, you know, forget it. What if you want to be, you don't want to be just totally illiterate, so maybe this is not for you. But more than that, what if you want to get it, but you come from an environment where this stuff is scary? And so I've added this slide because there's a university in the U.S., it's a girls' school, Bryn Mawr University. They get bright women as their students. No guys at Bryn Mawr. It's one of the few schools that's maintained the one-gender education. And what they do is, in the freshman course, the guy tells me there's no way he could start with my book. He'd scare them all away. So he starts with robots, and they write programs to manipulate the robots. And then once they get over that comfort level, then he uses my, my approach. More observation. Serious programming is about design. Yeah, no question. I don't even know why I even bother with this. I guess I do because too many people don't understand that. Programming, real programming, is design. You got a sheet of paper and you have to write a program. You're designing. Before you design, you should first understand the components. Scheme at MIT, I would argue, is misunderstood. People think scheme is top-down. It's not. It's bottom-up. That is to say, what they've done at scheme is they don't start with the transistor as a wall switch. They don't start at that level. They start at a higher level. But they start with this level for which they don't go below. They try to make it so the kids can't screw up understanding that level, and then they build. So the freshman course, 6001 at MIT, is all about algorithms, starting with that basic model and then moving up. Then once they get that, then they go down. So this I thought I'd throw out to you. If I had it my way, in fact, I used to do this at Berkeley, and the kids got it. Teach data structures with Knuth, okay? And the way Knuth does it, which is store the data structures. Don't have time for that. We have to use the high-level abstractions, and then the kids never get it, right? But what does a linked list look like? Do we care? I would argue if we're teaching professionals, then we should care. Okay, ripple effect on the curriculum. Doing it my way will affect the curriculum because there's a lot of intransigence among some of the older faculty, because if you start my way, then the kids know so much more at the end of this course that it really does affect everything that goes on after this. People can build. Right now we've got instructors teaching the second course that refuse to accept the fact that the kids have already had my course. And I get comments from the kids all the time. He says, why is this guy wasting our time? That's all he has to say is, boom, and we would get it because we've already had it in the first course. And we're gaining ground, as I say, Cornell, Purdue, etc. Everyone who uses it seems to like it. I think this is my last slide, which will make you happy. After more than 40 years in the trenches, I strongly believe that a simple concrete model really makes a big difference. We can think all we want about beautiful abstractions because we've been doing it for 20 years or 30 years or 40 years. We're not in the shoes of the kid who's just seeing it for the first time. We are not freshmen seeing it for the first time. And so even though we can make believe or something and teach these nice abstractions, There's no substitute, in my view, for this simple, concrete model. And I am done. Did I go over?
5 minutes.
Okay, good. All right. Thank you very much.